Okay, is your favorite TV program often interrupted by advertising? CNBC presented statistics on the average number of programming minutes in a half-hour sitcom. The following data in minutes are representative of their findings. So there's 20 data values there. Assume the population is approximately normal. Provide a point estimate and a 95% confidence interval for the mean number of programming minutes during a half-hour television sitcom. Okay, let me kind of explain something about the situation with confidence intervals, and I'm going to use sort of a Venn diagram approach. Suppose we have a population of values that we're interested in studying, and in this case the population is 30-minute sitcoms. And I'm interested in the average programming minutes. For 30-minute programs, the average number of programming minutes. Now, to do that, I'm going to take a sample of size, in this case 20. So 1, 2, 3, and I'm taking sort of a random sample of size 20 from this population. So from all of the possible sitcoms that play over and over again each week, I'm just taking a random sample of 20. And I'm going to calculate the average of that. And it turns out, if you put those values into Excel, it turns out that the average is 22 minutes. And the standard deviation on the sample, symbolized by using the letter S, is the sample standard deviation is 1.119. And what these two X bar and S, what these are called are the point estimates. In other words, the X bar points to and estimates the mu. We would have to have all the 30-minute sitcoms, all of them played over and over again throughout the weeks, to actually know what mu is, and that's impractical to really spend that much time and effort to do that. So what we relied upon is a sample. The 22-minute average is an estimate of the overall population average. It's a point estimate. It points to that overall average. S is actually a point estimate for sigma. Sigma is the population standard deviation. So again, there's a little bit of different symbolism indicating what the actual value is either representing or estimating. But what we want to do, and actually we've answered one question, what is the point estimate, or what's the an estimate for the average number of programming minutes? It's 22 minutes. What we want to do now is to answer a question like, how close are we? And it's interesting, in statistics, through the sampling distribution, we can answer that question. We can know how close we are to the original population average, mu, without knowing what it is. We have an estimate of it, 22 minutes, but we can know through probability of how close that 22 minutes is by constructing a confidence interval. Now, in the last section, the confidence intervals were built around the normal probability density function, the sampling distribution, and that was normal because our sample sizes were at least 30 or greater. In this section, we have a small sample size. Our sample size is 20, and 20 is less than or equal to 30. So we really can't for sure know that the sampling distribution is normal. We can't use our normal probability density function. Instead, we're going to use a t-distribution. This was another distribution developed for the small sample case. And our confidence interval, we're going to look at the formula x bar plus or minus t alpha over 2 and then use our standard error s over the square root of n. Again, this part of our confidence interval is our margin of error. And we will be able to know through that how close that 22 average is to the real population. And we're going to have in this problem 95% confidence. So we can, with 95% confidence, know how close we are to the real population average. Now, basically, as before, it's pretty much just fill in the values into this interval. So 22 plus or minus. Now, the T alpha over 2, we got a 95% confidence interval. So alpha is the probability of error, is 5%. So it's 0.05 divided by 2. So I'm talking about T sub 0.025. And that's going to help me find the number in the table that I need for my T alpha over 2. I'm going to look in the 0.025 column. Also, for the row is the degree of freedom. And what you do to calculate the degree of freedom is take your sample size and subtract 1. So in this case, our degrees of freedom is 19. Now what we do is we take the 0.025, 95% confidence, and our 19 degrees of freedom, and go to the table. The 19 is going to be the row that we're going to find our value in, and the 0.025 is going to be the column. So when I take those numbers to the table and look up my T alpha over 2 value, I'm going to get that the T sub alpha over 2 is equal to 2.093. So that's what I'm going to put in my problem. Now this was a normal distribution for a 95% confidence interval. That would just be 1.96. But again, these are small sample sizes. They're less than 30. So my margin of error is going to increase because the sample is pretty small. And sure enough, instead of using 1.96, I'm using 2.093. So that seems reasonable that the margin of error is going to increase. And again, it's all based on a mathematical model called a t-distribution that is an observation in how this kind of sampling works when you're less than 30. The sample standard deviation is 1.119, and the sample size is 20. So I'm going to divide that by the square root of 20. So I pretty much put everything into my confidence interval. And let's just carry that another step here. I got 22 plus or minus, my margin of error is 0.5237. I want to stop there just for a second. The 0.5237 is in minutes, so if I multiply that by 60, I'll get about 31.4 seconds. And I just make that observation to say that our 22, based on a sample size 20, our 22-minute average, as an estimate of the population average, is off by no more than 31 seconds. And I'm 95% sure of that fact. So I'm 95% confident that the real population average is within about 31.4 seconds of 22 minutes. Let me say that again. I'm 95% confident that the real population average, mu, is within 31.4 seconds of my 22-minute sample average estimate. So to build that into the interval, I just simply add and subtract that to the 22, and I get 21.48 on the lower end of the interval and 22.52 on the upper end. So I am 95% confident that the real population average number of programming minutes is somewhere between 21.48 minutes, or I suppose you could say just 21.5 minutes, to 22.52 minutes. I'm 95% confident that the real population average number of programming minutes is somewhere between 22 or 21.5 minutes to 22.5 minutes. So with my point estimate being 22 minutes as my best guess at this point, I know that I'm within about a half minute of the real value somewhere. So the confidence interval sort of tells me how close my sample estimate is to the real value. And that's pretty powerful. It's all based on probability. It's based on the sampling distribution. In this case, a t-distribution model for that because we are less than a sample size of 30. Also, again, notice that that table does work differently. So what you have to do is you have to figure out what your alpha is, and for 95%, that's a 5% error, that's alpha, and divided by 2 because the confidence interval has two ends of the distribution. So the number we look up in the column is 0.025, and the row is the number of the degrees of freedom. So the table works a little different to get the value that we need. The value we need in this case is the 2.093. On the test, make sure that you look at the condition for of the problem to determine whether you're going to be on the normal distribution or normal density function or whether you're going to need a t-distribution. So remember to check that on these problems to see which distribution is going to be the one to use.